All right, so implicit differentiation, it's a way of finding derivatives. What we're used to is equations that are in something called explicit form. An explicit form means y is by itself. So like y equals 3x cubed minus 6x plus 7. And these are really easy to take the derivative of, because what's the derivative of y? Y prime, right? Don't we call it y prime? Derivative of y prime. Okay. And that's equal to, what's the derivative of 3x cubed? 9x squared minus 6 plus 0. Okay. So there's my derivative. Okay, now other equations don't have to be written in explicit form. They can be written in something called implicit form. And implicit form is something that looks a lot messier, like xy minus 2x squared plus 3y cubed equals 6x minus 7y. And it's implicit form because the x's and y's are just mixed up. Okay, there's x's and y's on both sides of the equation and y's not by itself, and it's called implicit form. And usually our goal, what you've always been told to do, is get y by itself, right? Get y by itself, get y by itself. Well, guess what? Trying to get y by itself here could be a really big challenge. Okay? And actually, we don't even need to get y by itself to take the derivative. So, in order to be able to take implicit derivatives, or derivatives of implicit functions, implicitly written functions, functions that have the x's and y's on both sides, we are going to be asked to take derivatives of these today. And we don't have to get y by itself to do that. But we have to get one thing, one concept through our head in order to help us understand how to take an implicit differentiation, and that is the chain rule. Okay? Remember how I said the derivative of y? What's the derivative of y? Y prime. That's if it's just y. Okay? So the derivative of y is what we need to get past. We have to get over the hump, the derivative. How do I find the derivative of y? And not just y, but anything with y. So, how would I take the derivative of 3y cubed? Or negative 7y? Or how about xy? Anything that involves y is not, it's different, because y is typically assumed, to be a function of x. In other words, y is assumed to equal something that has an x in it, right? So when I say what's y, you assume it's like some equation like 2x minus 4, or the square root of x. So what we have to assume in our head as mathematicians, and if I'm finding this derivative, that y is some other function out there that we don't know. So what actually we're dealing with in a problem like negative 7y to take its derivative, y is some inside function. So like this would, this would even be a better one. If I'm taking the derivative of 3y cubed, y is assumed to be some secret function that I don't really know, like sine of x. And if I were going to take the derivative of 3 sine cubed of x, I would have to use the chain rule, because it would have an outside function, the 3 times something cubed, and the inside function, whatever y equals. So the way you have to treat a derivative of y is you have to use the chain rule. The derivative of, so like let's say I want to take the derivative of in terms of x. Remember, derivatives are always in terms of x, well, most of the time. It could be in terms of theta or t. But the derivative of y, other notations to write, remember, are the derivative of y, you could write y prime. Could you write dy over dx? Doesn't that mean the derivative too? The derivative is always in terms of x. So if I want to find the derivative in terms of x of 3y cubed, here's how I have to do it. I take the derivative of the outside function, which is what I see outside the y. So what would be the derivative of 3y cubed? Just leave it like, what's the derivative of 3y cubed? 9y squared. Okay, see how we did that? Just pretended it was an x, took the derivative. Now we have to assume that we have a chain rule. So that was the derivative of the outside times what would be the derivative of just the y? Y prime. What's the derivative of y? Y prime. So anytime you're going to do an implicit differentiation problem, okay, you're going to do one of these, it has x's and y's all mixed up. Whenever you take the derivative of y, whenever you take the derivative of y, something that has y, the sine of y, the cosine of y, the secant of y, 5y cubed, anything that has a y in it, you take the derivative and then times by y prime. Take the derivative, then times by y prime. So if I wanted to find the derivative in terms of x of the cosine of y, the derivative of the cosine of y, well, what's the derivative of the cosine of something? Negative sine of y times the derivative of y, which is y prime. Take the derivative, then times by y prime. Okay, take the derivative and then multiply by the derivative of y, which is y prime. Yep. Okay, so that's the main hurdle we have to get through. How do I take derivatives when there's y's mixed up in the problem? And that is, follow this set of instructions here. Now we have a main process that we want to be able to go through in order to find, solve an implicit differentiation problem. So this process, these steps are all in your book on page 142. I'm going to outline them here now, though. So these are your steps for implicit differentiation. Okay, and I'm going to try to write them and do an example at the same time. We'll see how that works. So I'll actually do that, well, I'm going to do a little simpler example. So here are my steps, step 1, and I'm going to do an example over to the side here. We'll be finding the derivative of x cubed minus xy plus y squared equals 4. And so step 1 is basically I just want to take the derivative, differentiate both sides with respect to x. Differentiate both sides with respect to x. And that's where you are doing what we just talked about. Whenever you take the derivative of the y part, you multiply by y prime. Take the derivative and then multiply that derivative by y prime. Okay, so that's what I'm going to do in my first step. So here's step 1 in my example. So what is the derivative of x cubed? 3x squared. Okay, now I move to the next term. And what rule am I going to have to use to find the derivative of the next term? Product, because I'm taking a negative x times a y. So I'm going to have to use the product rule here. And my first is going to be negative x, and my second is going to be my y. That'll make my life easier if I just put the negative with the first. Okay, so now I'm going to follow my product rule. I write the first, negative x, times what's the derivative of y? Y prime. Derivative of y. You can think of it another way. You can think of what's the derivative of y? It's 1 times y prime. Same thing. So y prime. Okay, now plus the second, which is y. Now, did I take the derivative of y there? So I don't write y prime. I only take it times y prime when I take the derivative of a y. So that's the second times the derivative of the first. What's the derivative of negative x? Negative 1. Okay. Now where am I at in the problem? Okay, so here I'm taking the derivative of plus y squared. So what's the derivative of y squared? 2y, so plus 2y times y prime, because I took the derivative of y. Equals, what's the derivative of 4? 0. Derivative of both sides. Okay, second, get all terms with y prime on the left and without y prime on the right. Doesn't really matter, but this way we'll all be consistent. So any terms that have y prime on the left and any terms without it on the right. So I guess first I'm going to clean this step up a little bit, make it look a little, not really, there's not much you can do. It's negative, or it's 3x squared minus xy prime minus y. That's the only part I can write a little nicer. And then plus 2y y prime. And make sure you make your y primes noticeably different from your y's, like you can tell it's y prime. So, which terms have y prime? Okay, so this one and this one, right? So I'm going to keep those over on this side. So negative xy prime plus 2y y prime. And the other terms, I'm going to move to the other side. So what happens when you move them from one side to the other? They change signs. So it's going to be y minus 3x squared. I just always choose to write the positive term first. If you wrote negative 3x squared plus y, it is the same thing, and I don't care. Okay? So, third step. Factor out a y prime from the left. Notice you got all the terms that had y prime on one side, so now you're going to factor that y prime out. And what is left inside? Writing the positive term first. 2y minus x. Okay, and finally the last step to get y prime alone. Remember, when you're finding a derivative, aren't you finding y prime? So when we found our derivative, we had y prime all mixed up in our whole problem, and we had to just get it by itself. Actually, we were done right here with the derivative. At this point, after step 1, you're done with the derivative. The rest of this is just algebra to get the y prime alone, so it looks like a normal derivative that you're used to seeing. So once you factor a y prime from the left, now you have y prime times some quantity. How do you get rid of times something? Divide. So all you're going to do now is divide both sides by the factor times y prime. The one, basically it's the one you factored y prime out, and it's whatever is here. A factor is something in parentheses. A factor is something you multiply. So now I'm just going to divide both sides by 2y minus x, and I'm going to get y prime equals y minus 3x squared over 2y minus x. And some people think they're going to be real cute here and start canceling things, and no, don't even go there. You'll be wrong. Okay? Things that are adding and subtracting on top and bottom don't cancel. So you're done. There's your derivative. So now we're going to look at a few more examples, and I'm going to throw in problems like find the equation of a tangent line, find the slope at a certain point, and we'll end up with the second derivative implicitly. So basically these are the steps. We're just going to look at examples now. It's just another way to find derivatives. This uses the quotient rule, the chain rule, the product rule. All of our rules still apply. Sum and difference rule. But now we can find derivatives without having y by itself.